All right, part one, mathematical background. Before we tackle cryptography, we need to cover some basic facts from mathematics. Much of the following can be found in a number of university discrete mathematics courses aimed at computer science or engineering students. So I've taught discrete mathematics aimed at those groups at Purdue University Calumet, by the way, years ago. All right, so this aimed at computer. Hence, one hopes not all of this section is new. For those who want more formal definitions of concepts, there is Appendix A at the end of the book. I could probably make a Udemy course on discrete mathematics if there was an interest in that. This part is mainly a quick overview to allow you to start on the main book proper. Hence, you may want to first start on Part 2 and return to Part 1 when you meet some concept you are not familiar with. Chapter 1, Modular Arithmetic, Groups, Finite Fields, and Probability. Chapter Goals: to understand modular arithmetic, to become acquainted with groups and finite fields, to learn about basic techniques such as Euclid's algorithm, the Chinese remainder theorem, and Legender's symbols. I think that's how you say that, Legender. To recap on basic ideas from probability theory. All right, Section 1, Modular Arithmetic. Much of this book will be spent looking at the applications of modular arithmetic, since it is fundamental to modern cryptography and public key crypto systems in particular. Hence, in this chapter, we introduce the basic concepts and techniques we shall require. By the way, modular arithmetic fits properly in the field of number theory. The idea, well, I've also seen that in other places. Okay. The idea of modular arithmetic is essentially very simple and is identical to the clock arithmetic you learn in school. For example, converting between the 24-hour and the 12-hour clock systems is easy. One takes the value in the 24-hour clock system and reduces the hour by 12. For example, 1300 in the 24-hour clock system is 1 o'clock in the 12-hour clock system, since 13 modulo 12 is equal to 1. Right? Take 1, add 12 to it, and you'll get to 13. More formally, we fix a positive integer n, which we call the modulus. In this case, the modulus is 12, right? For two integers, a and b, we write a equals b mod n if n divides b minus a. So here he said 13 equals 1, and 13 minus 1 is 12, and 12 divides into 12. Okay, so for two integers, a and b, we write a equals b mod n, like 1 equals 13 mod n, if n divides b minus a. And we say that a and b are congruent modulo n. Often we are lazy and just write a equals b. Like up here, he would write 13 equals 1, or 1 equals 13. If it is clear we are working modulo n. We also consider parentheses mod n as a postfix operator on an integer which returns the smallest non-negative value equal to the argument modulo n. For example, 18 mod 7 equals 4. Well, let's see. b minus a is 18 minus 4, which is 14. And 7 divides into 14 twice, right? So 18 equals 4 mod 7. Negative 18 mod 7 equals 3. Well, let's see. Negative 18 minus 3 is negative 21. And 7 divides into negative 21, so that's true. To go from 18 to 4, if you subtract 7, you get 11. Subtract 7 again, and you'll get 4. So basically, you shift 18 by multiples of 7. You'll get all the numbers it's congruent to. The modulo operator is like the C operator %, except that in this book we usually take representatives which are non-negative. For example, in C, or Java, we have parentheses -3 %2 equals -1. Let's see, so -3 mod 2 equals -1. Yeah, because if you add 2 to it, you get to -1. Or think of it as -3 minus -1 is -2, and 2 divides into -2. So -3 is congruent to -1 mod 2. So this % is the modulo operator in C or Java. Okay. All right, so whilst we shall assume that -3 mod 2 equals 1, Oh, sure. You add 2 to that. For convenience, we define the set Z mod NZ, or Z slash NZ, equal to 0 ... and -1. So I think this is equivalence classes, right? Splitting the integers up into those. So essentially it collapses the integers to the numbers 0 through n-1. Okay, so which is the set of remainders modulo n? Z mod nz, the numbers 0 up to n-1, and that's the set of remainders modulo n. This is the set of values produced by the postfix operator mod n. Right, the mod is the % symbol. Note, some authors use the alternative notation z sub n for the set Z mod NZ. What is that, like coset notation? However, in this book, we shall stick to Z mod NZ. The set Z mod NZ has two basic operations on it, namely addition and multiplication. These are defined in the obvious ways. For example, 11 plus 13 mod 16 equals 24 mod 16, which equals 8. You subtract multiples of 16 from this to get down to 8, right? And you could check that. 24 minus 8 is 16, and 16 divides into 16. All right, so 11 plus 13 mod 16 equals 24 mod 16 equals 8, since 24 equals 1 times 16 plus 8. See, 24 equals 1 times 16. Right, multiples of 16 plus 8. 8 is a member of that set from 0 to n-1. In this case, n is 16. So basically it's reduced. So 24 equals 1 times 16 plus 8. All right, 11 times 13 mod 16. So 11 times 13 is 143. So 143 mod 16 is 15, right? Since take multiples of 16, in this case 8 of them, and then you add 15 more to get 143. 15 is like the remainder. And notice 15 is from the set 0 to 16 minus 1. It's always reducible like that. So 143 mod 16 equals 15, since 143 equals 8 multiples of 16 plus 15. So 15. Okay, so what is that? The residue class mod 16? All right, section 1.1.